We mentioned methane a few times, but we haven't explicitly dealt with it so far in this course. So in this primer, not really a course. So we will go through this in this section of the book, where we will look at sources, sinks, some reactions that produce methane, some reactions that remove methane, and what the future may look like, or whether we can say anything about the future of methane in the coming decades and out to, let's say, 2100. Methane is like the radical wing of the carbon cycle in climate. This chapter summarizes the methane cycle and its potential for changes in the Anthropocene. That's kind of the tagline. We know that carbon dioxide, this book, this number is already quite old, is the major greenhouse gas, and then we have tropospheric ozone, halocarbons, so these are all the refrigerants and so on, nitrous oxide, and there is methane. Obviously, for all of these, we already said a few times that we just don't look at the percentages or the fraction of the total, but we also have to look at their residence times, how long they stay in the atmosphere once you put them out there, and what their global warming potential is. Global warming potential is done by the IPCC in terms of same weight, and considering a certain period of time, like 100 years. So if you put same amount of methane for 100 years as CO2, what is the relative warming due to methane in terms of radiation balance and greenhouse effects compared to the carbon dioxide? So carbon dioxide is used as reference 1. So methane has a global warming potential in that sense of weight by about 25 times, but the residence time of methane is just about a decade to 12 years compared to carbon dioxide, which has multiple centuries, as we already saw. So that's critical. If you do it in molecular level, you'll get different numbers in terms of global warming potential. But just remember that methane is in a much smaller concentration. Here, for example, it's 1.7 ppm, whereas here it's now we are at 420 ppm, so it's order of magnitude difference, but methane has also increased over time, as we will see. The other thing we need to remember in the context of the ice age and interglacial that we are in now is that methane has had similar positive feedback cycles as CO2 at ice age timescales. We saw that in the Vostok ice core with the sawtooth pattern, where methane and CO2 are following the same pattern in terms of slowly decreasing over the ice ages and then rapidly increasing during the deglaciation. I'm just showing here a different time scale just for fun. So this is the Danskard-Ushger events. Number of them are counted here over the period of 10,000 years to 80,000 years before present. So basically during the last ice age into the deglaciation here at the end, where methane increased from let's say about 350 parts per billion by volume to pre-industrial or 10,000 years ago of about 700 ppb, and over the Industrial Revolution it increased to about almost 1800 ppb, I think, at present. These are two data sets from two sites, but you can see that there is a strong correlation between temperature anomalies and methane anomalies, so it is also a positive feedback at ice age timescales, unstable as we called it for the carbon cycle. Focusing much more recently into the zero common era to the 2000s, there is carbon dioxide in parts per million. N2O and methane are in parts per billion. They are much smaller amounts, but you can see that methane shows an increase here to almost 2000 ppb by volume, and nitrous oxide is here also increasing from about less than 800 to about 1200. So these are the things we are dealing with. there are some nice schematics or what do you call these, informatics, infographics, sorry, from CCAC, the Clean Air and Climate and Clean Air Coalition. It considers methane as one of the short-lived climate pollutant. I have a course on bending the curve, which is all about short-lived climate pollutants and how they can be reduced for immediate impact on reducing warming and so on. So the substance here include black carbon, methane, tropospheric ozone, and hydrofluorocarbons. Just focusing on methane, anthropogenic sources include livestock, cattle, sheep, and ruminants, wetlands, which are a big sink and source, fossil fuel, unintended leakages, or sometimes intended leakages because they are too far from where they can be used. So methane is produced as a byproduct of oil exploration, let's say. So they won't be piped because it's not economically viable. So they are either released into the atmosphere as methane or burned off. So you will see lots of flaring of methane in various places. So that's again oil drilling there. That's what I'm talking about. And of course landfills, which are a big source of methane, and the lifetime in the atmosphere is about 12 years. Impacts tend to be local and also global, because in 12 years you can do plenty of global impacts. And obviously the faster life cycle or shorter residence time means it's getting converted to something, and methane is highly oxidizable. You can easily burn it, obviously you know it because it's a fuel, and that just converts it into carbon monoxide, carbon dioxide. So you reduce the greenhouse warming potential by converting it to CO2, but it's still greenhouse warming. Some additional points just to run through. Global methane budget for 2008 to 2017. There are things done bottom up, so fossil fuel production and use, emissions and sinks, agricultural waste, so you can see the numbers there. Biomass and biofuel burning, wetlands, other natural emissions, and sinks from chemical reactions in the atmosphere. So this, there is natural sinks in the soils as well, but the scrubbing from the atmosphere is important radical reactions that we will look at in some detail. So here are the total emissions, and here are the total sinks. Okay, so there are two estimates, bottom up and top down. That's what the two numbers you can see here. The change in atmospheric abundance is greater than 100 or 13 with a star here, which depends on how you did it. So obviously it's now part of the global warming concern. This is the same thing done as emission by source, so I won't dwell on it again. Okay, so methane, this is from the Climate and Clean Air Coalition that I just mentioned, just showing kind of the percentages. Agriculture, 42% includes livestock, 36% is from fossil fuel operations. I will show this again. 18% from waste and landfill, and 3% are others. In terms of impacts, responsible for 40% of the warming since Industrial Revolution, 84 times more powerful than carbon dioxide over a 20-year period. So this is not done by weight. This is done by molecular level radiation impacts, absorption spectra, and so on. So you get very different numbers. So make sure you understand this. In all the IPCC reports, you will see greenhouse warming potential as about 25 or 26. Okay. Health impacts are huge. Increasing emissions are driving a rise in tropospheric ozone. We'll see how that reaction happens. Air pollution causing 1+ million premature deaths annually. So the methane decomposition happens by the OH radical, which has all these complicated interactions with oxygen, water, nitrous oxides and then producing ozone is part of this overall reaction. Respiratory diseases, heart diseases, damages to airways and lung issues, and agriculture and ecosystem. There is a impact on them in terms of up to 15% yield loss, because ozone production actually leads to crop yield losses, even though there are some debates about it. So we'll look at a little bit more about the methane's impact on radiation balance by going through some details, especially compared to CO2. We'll do that in the next podcast. Okay.